Today, our topic is comparison of MOSFET with JFET. So, previous classes we studied about JFET as well as MOSFET. So, JFET is two types. One is N-channel JFET and other one is P-channel JFET. So, we will see the in detailed in transfer characteristics and drain characteristics in JFET. And also we will see in MOSFET. So MOSFET is two types. One is depletion MOSFET, other one is enhancement MOSFET. So MOSFET is also called as IGFET. IGFET means insulated gate field effect field effect transistor. So that is called IGFET, and also we call it as MOST. MOST means metal oxide silicon transistor. So we've seen in detail in previous sessions. Now we will see the comparison of MOSFET with JFET. So in enhancement and depletion types of MOSFETs, the transverse electric field is induced across an insulating layer deposited on a semiconductor material, controls the conductivity of the channel. That is called MOSFET. Only field is established in MOSFET, whereas in JFET, the transverse electric field across the reverse biased PN junction controls the conductivity of the channel. So in MOSFET, the conductivity is controlled by induced insulating layer deposited on a semiconductor, whereas in a JFET, the conductivity is controlled by a reverse biased PN junction. Okay. In the output characteristics of JFET are flatter than those of MOSFET. We will see in JFET characteristics are very flatter compared to the MOSFET, and hence the drain resistance of JFET is much higher than that of MOSFET. Okay, JFETs are operated only in depletion mode. So what do you mean by depletion mode? Depletion mode is nothing but current conductivity is decreases. What about enhancement? Enhancement means current conductivity is increases. Enhancement means increases. So in JFET are operated only in depletion mode. The depletion type MOSFET may be operated in both depletion mode and enhancement mode. So comparing to JFET and MOSFET are easier to fabricate. So what is the main advantage between FETs and BJT means the size. The size of MOSFET is very small compared to BJT. That's why in many integrated circuits like VLSI, we are preferring MOSFETs so that we can accommodate more number of FETs in a single chip. So that is the main advantage of MOSFETs or JFETs. So MOSFETs are very susceptible to overload voltages and need special handling during installation. So MOSFETs are widely used in digital VLSI circuits. VLSI means very large scale integration circuits. At present, GLSI, gain scale integration. So these MOSFETs are widely used in VLSI circuits. VLSI means very large scale integration circuits than JFET because of their advantages. So these are the main differences between MOSFET and JFET. Now we will see the small signal analysis of JFET. So in small signal analysis, we have three parameters. One is drain current, other one is drain source voltage, and other one is gate source voltage. We have three parameters, that is ID, VDS, and VGS. So the functional equation can be written as ID is equal to F of VDS comma VGS. That means drain current is a function of VDS and VGS. That is, drain current is a function of drain to source voltage and gate to source voltage. So both the drain and gate voltages are varied. That means VDS and VGS are varied. The change in drain current is approximately first two terms in Taylor series expansion. So we are reducing higher order terms in Taylor series. Only we are taken lower order terms. Okay. So we are changing VDS and VGS and find the ID value. That means drain current value. So we have three parameters. We have to fix one parameter and other parameter is varied. Corresponding drain current we will note. Okay, that is the thing. So first we will see Taylor series expansion. In Taylor series expansion, so change in ID, this one, change in ID, delta ID is equal to change in ID by change in VDS. That means dou ID by dou VDS at VGS is constant. We know that three parameters, we have to fix one parameter as a constant value and vary the VDS, means drain to source voltage, and a corresponding ID value can be noted. That is the first thing. So dou ID by dou VDS at constant VGS into change in VDS. Similarly, dou ID by dou VGS at constant VDS into change in VGS. So this is the first lower order term of Taylor series expansion. So we are changing gate to source voltage in this first first expression, and second we are changing gate to source voltage and fixing VDS is equal to constant. So here VDS are changing and VGS are changing, corresponding ID, change in ID we are measuring. So that is called Taylor series expansion in lower order terms. So here change in ID we can rename as small ID. Similarly, change in VGS is equal to small VGS. This is small VGS. VGS means gate to source voltage, and change in VDS is equal to change in VDS, small VDS, that is drain to source voltage. So we know that we have to substitute here. Change in ID is identical is equal to small ID, drain current, and VGS, change in VDS, delta VDS can be written as, so this is change in VGS. Change in VGS can be written as small VGS. So here GM means transconductance, that is dou ID by dou VDS is called as transconductance, denoted by GM. GM is nothing but transconductance. The units of transconductance is mho. Okay. Next, other term is dou ID by dou VGS. That means it is inverse of resistance. So we can write it as 1 by RD. That is drain resistance. Dou ID by dou VGS. We can write it as 1 by RD. So change in VGS, delta VGS, we can write it as small VGS. Delta VGS can be written as small VGS. So finally, we will get ID, drain current, is equal to GM into VGS plus 1 by RD into VDS. That means drain current is a function of VDS and VGS. That means drain to source voltage and gate to source voltage. We have three parameters. We have to fix one parameter as a constant and vary the other parameters. Corresponding ID current we will note down. That is called small signal analysis. So finally, we will get ID is equal to GM into VGS plus 1 by RD into VDS. So we know that transconductance GM is equal to dou ID by dou VGS at constant VDS. So we have to fix VDS is equal to some constant value and vary the gate to source voltage and corresponding ID we will measure. So that is transconductance. So this is identical is equal to change in ID by change in VGS at constant VDS. So small signal analysis, we have to write the all values. Capital ID can be written as small ID, and capital VGS can be written as small VGS at constant VDS. So that is transconductance. So similarly, drain resistance. So we know the basic formula. V is equal to IR. That is voltage is equal to current into resistance. From this, resistance is equal to V by R. Resistance is equal to voltage by V by I. R is equal to V by I. That is voltage by current. Same way, so resistance, drain resistance RD is equal to dou VDS by dou ID. That is change in VDS, change in drain source voltage by change in drain current. So voltage by current at constant VGS is identically change in VDS by change in ID at constant VGS. So it is a small signal analysis means we have to write in small letters like uh, capital VDS, change in capital VDS can be written as small VDS. So change in ID can be written as small ID at constant VGS. So this is drain resistance. We know that what do you mean by mu? Mu is nothing but amplification factor. Mu is nothing but amplification factor is equal to dou VDS by dou VGS at a constant ID. Here drain current is constant. We are varying VGS and corresponding VDS value we have to note down. So change in VDS by change in VGS at constant ID. So small signal means we have to write VDS by VGS at ID is equal to 0 or some other value. ID is equal to 0. Next time ID is equal to 1. Next time ID is equal to 2. Likewise. So finally we will get mu is equal to RD by mu is equal to RD into GM. That is amplification factor is equal to drain resistance and is multiplied with transconductance. Drain resistance is multiplied with transconductance is called as amplification factor. Is called as amplification factor. So already we know that this equation, this is small signal analysis equation. So drain current. So drain current is equal to GM VGS plus 1 by RD into VDS. So this equation can be written in a circuit form like this. So same equation can be written as small signal circuits, small signal analysis. So we know that so ID is the drain current. What do you mean by GM and VGS? GM is the transconductance and VGS is nothing but gate to source voltage. So we can represent it as this term GM VGS can be represented as this one. So GM VGS. So that means VGS gate to source voltage is proportional to the transconductance. Proportional constant is transconductance. So this term will not write it as this one. So this symbol we call it as dependent source. Dependent source. This symbol and 1 by RD into VDS. So this is R and this is VDS value. So this term we will write it as like this RD into VDS. So you can observe here source is the common terminal here. Source is the common terminal. So anyway this is ground here. So source is common terminal. That's why it is a common source amplifier. So source is common to both. So this is the input side. This is the input side. This is the output side. So here source is grounded. That means source is common to both input and output. That's why it is a common source amplifier. Common source amplifier. So this is a low frequency model for FET, has a Norton's output circuit with a dependent current generator whose magnitude is proportional to the gate to source voltage. So we know that what do you mean by Norton's circuit? What do you mean by Thevenin circuits? So Thevenin circuit is look like this one, voltage source and uh, series with resistance. So this is VTH, this is RTH. That is called Thevenin circuit. This one we call it as Norton circuit. So Norton circuit is nothing but a dependence voltage source. Dependence voltage source is connected with the parallel resistance. That is called Norton circuit. So this low frequency model for FET has a Norton's output circuit because it is look like Norton circuit. One dependent source, parallelly one resistance. That is called Norton's output circuits with a dependent current generator whose magnitude is proportional to the gate to source voltage. Okay. So the proportionality factor is transconductance here. The proportionality factor is transconductance, that is called GM. GM is nothing but transconductance, which is measured in mhos. Okay, so the output resistance is RD. RD means drain resistance because it is a drain terminal. Output side resistance we call it as drain resistance RD, or also called it as R0. R0 and RD are same because output resistance in common source output resistance is drain resistance, which is denoted by RD, and also we can write it as R0. So output resistance R0 or RD. So the input resistance between gate and source. So here gate. So input resistance means this one is the gate, this one is the source. So input resistance between the gate and source is infinite because there is no resistance is connected across input side. That's why resistance is input resistance is infinite, since it is assumed that the reverse biased gate draws no current. Okay, understood? So this is called a small signal analysis common source amplifier. Okay, I repeat, please concentrate. We have in small signal analysis, ID is equal to GM into VGS, GM into VGS plus 1 by RD into VGS. So this equation can be written as two-port networks like BJT. We are writing small signal analysis. Same way we are writing here. So ID is the drain current. ID is the drain current and GM VGS. So this is the GM VGS and plus 1 by RD. So RD term, resistance term and VDS. So this is called small signal analysis. Here source terminal is common to ground. So source terminal is common to both input and outputs. That's why we call it as common source amplifier. So so this is whole. We can write it as a transistor. This is a FET. This is a FET. Okay. So this Norton's output look like it is a Norton's output. See, you can observe it is a, we know that it is a FET. So this is the gate terminal, drain terminal and source terminal. So FET is a three terminal device. What are they? Gate, source and a drain. So the conventional current direction is out of the bar. That means it is a P channel. That means it is a P channel. If the conventional current direction is into the bar, that means into the bar means it is like this. So that we call it as N channel. That we call it as N channel FET. So the same FET circuits can be replaced in small signal analysis like this, like previous circuit. So one dependent source is multiplied with transconductance Gm into here Rd. Here R naught. R naught is nothing but output resistance. R naught we can also call it as Rd. Rd means here drain. So because it is a drain terminal, it is a source. Source is common. Source is common. Okay. This is the ground. So source is common to both input and output. Source is common to both input and output. So this is transistor equivalent circuits in small signal analysis like this. So same transistor can be replaced with this circuit. That is called small signal here. Here one amplifier circuit. So it is a common source amplifier. So because it is a drain terminal, source terminal, and a gate terminal. So here source is common. That means source is ground. So this transistor symbol can be replaced by small signal circuits. So this is the circuit. Whole circuit we call it as it is a transistor. It is a transistor. So this transistor is replaced by this one, small signal analysis. Okay. So remaining this one R1 and R2, these are parallel means R1 parallel R2. So it is a node. So R1 is parallel to R2 means we can write it as R1 parallel R2. And the remaining same as it is. So source resistance and input voltage. Source resistance and input voltage and one capacitor. Okay. This is called small signal analysis. So from this small signal analysis, we can calculate many parameters like current gain, voltage gain, input resist impedance, output impedance. So like BJT, we are calculated many parameters like voltage gain, current gain, input impedance including source, input impedance excluding source. Like that, we have calculated many parameters in BJT. Likewise, we will calculate here also input voltage gain. So voltage gain means output voltage by so voltage gain, that is AV. AV is denoted by output voltage V naught by input voltage. Here what is output voltage? Output voltage is VDS. So VDS by what is input voltage here? VGS. Likewise, we have to calculate the all parameters in small signal analysis. So this is called a common source amplifier. The circuit we call it as a common source amplifier, which is write down in small signal analysis, and we have to find out the different parameters are voltage gain, current gain, input resistance, output resistance, input resistance with source resistance. Likewise. Okay, this is called common source amplifier, which is called common source amplifier. Okay, so in this class, I will summarize what we discussed in this session. So in this session, we talked about the differences between the junction FET and MOSFET. So there are many advantages in MOSFET because it is a small in size, so that we can use in VLSI fabrications. FET is more preferable, and it is also very less noise compared to JFET also. Okay, so the conductivity is depends on the field, induced field in MOSFET, whereas junction FET, the conductivity is depends on the junction. The conductivity is depends on the junction. Okay, these are the main differences in JFET versus MOSFET, and we will see in the small signal analysis in JFET. So in small signal analysis, we have three parameters. One is drain current, other one is drain to source voltage, and gate to source voltage. So among three parameters, we have to fix one parameter and vary other parameters, and corresponding ID current we will note down. So by using Taylor series expansions, we have calculated the change in the drain current equations. So finally, we will get amplification factor is equal to transconductance into drain resistance. Transconductance into drain resistance. So from that we are calculated small signal circuits. And small signal circuit is nothing but Norton's equivalent circuits. So that means dependent source VGS, dependent source VGS is proportional to the transconductance. Okay, dependent source VGS is proportional to the transconductance, and the terminal source terminal is ground, means that is common to input side and output side. That's why we call it as common source amplifier. That's why we call it as common source amplifier. Then we have to measure other different parameters like voltage gain, current gain, and input impedance, output impedance, input impedance with source resistance, input impedance with without source resistance. We have to calculate all the parameters. Okay, this is called small signal analysis in common source amplifier. Okay, okay, thank you.